This video is on Unit 3, Chapter 7, Rational Exponents and Radical Equations, Lesson number 4 on inverse relations. In your notes here for inverse relations, it has a notation that the inverse of a relation R is written as R raised to the negative 1 power, or inverse of R. To find the inverse of a relation, all we have to do is switch the x and the y values. And I want to add something here that a relation is just simply a set of ordered pairs. Again, a relation is just a set of ordered pairs. A one-to-one relationship. So a function has a one-to-one relationship if the relation and its inverse are both functions. So they both have to be a function, the relation and the inverse. So looking at example number 1, we have the relation 1, -2, 2, 4, 3, -1, and 4, -2. And we're supposed to identify what the inverse of that is. So the inverse of R is going to be -2, 1. Again, all I'm doing here is I am reversing the x and the y values in each ordered pair. So there's the inverse. So it asks us, is R a function? Well, in order for something to be a function, the x's cannot repeat. Put very simply, if a relation is a function, then the x's will not repeat. So if I look at the relation itself, I'm looking at 1, 2, 3, and 4. So because there are no x's that repeat themselves, the relation R is a function. So that's a yes. Now it asks me, is the inverse of R a function? So here again, I'm going to look at the inverse of the relation, and I'm going to look at the x's. And because there are two ordered pairs that have a repeating x, the inverse is not a function. So it asks then, is R 1-to-1? And that would also be no. Remember that in a one-to-one relationship, the relation and its inverse must both be functions. So let's look at example number, let's jump to number 3. So looking at number 3, we've got this mapping. It's called a mapping. It has an oval representing the x's. It has the oval representing the y's. And then the arrows give us the ordered pairs. So for the relation, I would have 0, 6, 1, 2, and 11, 6. So those are the ordered pairs that are represented in that mapping. Now we need to state the inverse, the inverse of the relation. So 6, 0 is one ordered pair, 2, 1, and 6, 11. So then the question is R a function? So is my relation a function? And again, the x's are not repeating here, so that would be a yes. And then it says, is the inverse of R a function? And this again is going to be a no because we have two x's that repeat. And then is it 1-to-1 is also going to be a no because in order to be 1-to-1, both of those answers would have had to have been a yes. Under horizontal line tests, the very first bullet is a recall. So you've got to remember, probably from Algebra 1, maybe even geometry, that the vertical line test is used to determine whether a relation is a function given a graph. So if we're looking at a graph, what we're going to try to do is imagine a vertical line going through that graph. As long as we only hit one point on the graph, then it is a function. So your vertical line test, again, you can only hit one point. I'm going to put can only hit 1 point. If you hit more than 1 point, your relation is not a function. So sometimes the relations can be a graph of a line or some kind of an equation is graphed. And we can use our vertical line test to tell whether or not that equation represents a function. The horizontal line test, I'm looking at the second bullet, the horizontal line test is used to determine whether the inverse of a relation is a function. So you've got to keep this straight. Vertical line test tells me whether the relation is a function, and the horizontal line test tells me whether or not the inverse of the relation is a function. And here again, you're only allowed to hit 1 point on the graph of the equation in order for that to be a function. If you hit more, then it's not a function. Both the relation and its inverse must be a function in order to be a one-to-one function. So let's look at these two examples here. It says determine whether the relation shown represents a one-to-one function. So looking at question number 4, if you can imagine taking a vertical line through that graph. So I'm going to draw just a vertical line. I'm going to hit 1 point, and that's it. There's no way for me to ever draw a line through this, a vertical line, through that graph and ever hit more than 1 point. So the relation is a function. Now, to determine whether or not the inverse of the relation is a function, we can use the horizontal line test. So again, we're going to imagine a horizontal line going through this graph. Is there any way for me to ever hit more than 1 point? And the answer to that is no. There's no way. There's no way I can draw a horizontal line and ever hit more than 1 point. So what I can take away from this is that the inverse of the relation is a function. So the question is then, is this an example of a one-to-one function? Yes, this is a one-to-one function. On number 5, looking at the graph of this, it looks like it's some kind of a version of maybe a sine or a cosine function that has been transformed and I've gone through some transformations. And what we're looking at here is, again, the question just says, determine whether the relation shown represents a one-to-one. So in order for it to be one-to-one, the relation itself must be a function, and its inverse must be a function. So I'm going to just say R. Is the relation a function? Well, if you imagine a vertical line going through here, is there any way to ever hit more than 1 point? No, there is not. I can only hit 1. So the relation is a function. What about its inverse? Is the inverse of the relation a function? Well, if I draw a horizontal line through here, I can hit 3 different points. So the inverse is not a function. So then to answer our question, is it one-to-one? No, this is not a one-to-one function. All right, moving on. Inverse functions, the notation, the inverse of a function f of x is written as f, and it's like an exponent of -1 of x. So that's f inverse of x. To find the inverse of a function, the first thing that you're going to do is you're going to replace the f of x with the y. You're going to interchange or switch the x and the y and then solve for y. And then you have to make sure that you write your answer in the correct format. You want to rewrite it as f inverse of x. And this last step is very important because it's actually going to tell us what the inverse of the given function was. So if you don't label it as such, I'm not going to know what I'm looking at. So make sure that you label things correctly. In our examples here, in number 6, it says f of x is equal to 5x. So we'll start out easy. We're going to change the f of x to a y. We're going to swap the x with the y because that's what's happening here. In an inverse function, your x's and your y's are going to switch. So in an equation, it's the same. And then we want to solve for y. So we're going to divide by 5. And we get y equals, and we can write this as x over 5 or 1/5 x, however you want to write that. And then we're going to put it in the correct format. So f inverse of x is equal to 1/5 x. Let's jump to example number 8. Let's look at number 8. So number 8, again, change your f of x to the y. Swap the x and the y. And then you have to use your inverse operations or opposite operations to get that y by itself. And this goes back to those literal equations that we studied all the way back in chapter 1. To get the y by itself, the first thing I'm going to start with is multiplying both sides of this equation by 3. And that gets rid of that denominator. And I end up with, I'm coming over to the side, 3x equals y minus 8. And then I can add the 8 to get the y by itself. And again, the last step is to make sure that you put the function in the correct format. So that says the inverse of f inverse of x is equal to 3x plus 8. And I would like to point out that back on example number 6, you've got in the original relation 5 times x, right? In the inverse of it, basically you got x divided by 5. And what I'm trying to point out here is that multiplication and division, are inverse functions of each other. So it should make sense that if we're finding the inverse of 5 times x, that it's going to involve division. The same thing happens in number 8. So number 8, the x is being divided by the 3. The opposite of that is multiplying by 3, which is what we have. And the 8 was being subtracted, and the opposite of that is add. So there are certain things that we can kind of look for if in a certain situation where you're trying to identify whether or not things really and truly are opposites or inverses of each other. You're looking for those opposite operations. I want to look at number 10. So again, we want to change the f of x to y. And then we're going to swap. And then we got to try to solve for y. So we're going to add the 9. That was easy enough. Now, how am I going to get just y by itself? If it says y squared, the opposite of that would be to take the square root. And we get y equals the square root of x plus 9. And again, we want to make sure that we have the correct format on our answer. So f inverse of x is equal to the square root of x plus 9. Number 11 is very similar to that. Again, changing the f of x to y. Swapping. And then we got to get the y by itself. We're going to start outside, and we are going to add the 6. And then we need to undo a cube. So we are going to take the cube root. and that's going to give me the cube root. I'm going to run out of room here. Is equal to just y plus 4. And then we need to subtract that 4. And when we subtract the 4, be very careful as you're writing this. Make sure that the minus 4 doesn't end up looking like it's a part of the radical. So that minus 4 is definitely an outside part of the radical. So f inverse of x is equal to the cube root of x plus 6. And then, of course, our minus 4 is out on the end. On this last section, it says verifying inverses using compositions. So composition of functions is also another concept that we saw back in chapter 1. Two functions, f and g, are inverse functions if and only if f of g of x is equal to x and g of f of x is equal to x. So basically what they're saying here is I have to be able to take one function, substitute it into the other one, and when we reduce everything, it's going to come down to just an x. And then same in reverse and vice versa. So the other function has to be able to be substituted into that first function, and its result has to be x. So let me show you what that would look like. So for f of g of x, we're going to put the g function, which is the square root of x minus 8, into our f of x. And this is going to look like this. So I'm going to take the x squared plus 8, and instead of an x, I'm going to have the square root of x minus 8 squared plus 8. So again, all I did was I put the g function into the f function. Now this is supposed to equal x. The square root and the square are going to cancel each other out, and we're going to be left with just the x minus 8, bring down the plus 8. The negative 8 and the plus 8 are going to cancel, and I'm left with just x. So that checks out. And then we have to do the reverse of that. I'm going to take the f function and plug it into the g function. So in the g function, I've got the square root of x minus 8. So I'm going to put x squared plus 8, which is my f function, along with the minus 8. And then I'm going to reduce. The negative 8 and the positive 8 are going to cancel, and I've got the square root of x squared, and the square root of x squared is just x, and therefore that checks out. So it's asking me here, is this, are these two inverses? And the answer to this, because they both situations equal an x, they are inverses. So yes, they are inverses. Just ignore that phone. Number 13, if you do number 13, actually I'll do number 13. So if f of x is equal to negative 4x plus 5, and g of x is equal to x over 4 minus 5. And we're being asked, are these two inverses? And we're going to again start with f of g of x. So the g function, which is x over 4 minus 5, is going to replace the x in the f. So I have negative 4 times x over 4 minus 5, and then plus 5. So I'm going to distribute the negative 4 first. Negative 4 times x over 4, those 4's are going to cancel, and I'm going to have negative x. Negative 4 times negative 5 is a positive 20, and then bring down the plus 5. So I can see really quick here that this is not going to equal an x. So because this is not an x, this does not work. These are not inverses. No, they are not inverses. I don't have to check the other one. I don't have to check g of f of x because I know that one of them is not equal to the x like it's supposed to be. So because that didn't work, they are not inverse functions of each other. So there are your notes for Unit 3, Chapter 7, Lesson number 4.